Hello, and welcome to our asynchronous session on greatest common factor and least common multiple. I'd like to begin with a lesson overview, including a video from Schmoop explaining the concept.
We speak student!
LCM and GCF a la Schmoop. Just what are these mysterious acronyms? Top secret government organizations? A new form of text speak? Or perhaps some misplaced Scrabble tiles? Actually, they're abbreviations for mathematical concepts. Well, LCM is an acronym for least common multiple. Let's take a look at that one first. Ooh, not so close. Let's back it up a bit, boys. Beep, beep, beep. There we go. First, we need to talk about what a multiple is. Say you've got the number 6. A multiple is any number that can result from multiplying our given number by any other number. For example, you can multiply 6 by 1 to get 6, by 2 to get 12, by 3 to get 18, by 4 to get 24, and so on. 6, 12, 18, and 24 are all multiples of 6. If you want to find the multiples of 8, you can multiply 8 by 1 to get 8, by 2 to get 16, and by 3 to get 24. We could keep going, but we can see you're in a hurry. If you want to find the least common multiple of 6 and 8, you need to find the smallest number that shares both numbers as factors. As you can see, it's unfortunately not as easy as merely multiplying the numbers together. GCF, or greatest common factor, is basically the reverse. When looking for a GCF, you need to find the largest number that will divide evenly into two other numbers. Take the numbers 36 and 48. Okay, wise guy, put them back. Suppose you were given the numbers 36 and 48. What factors do they have in common? Well, both numbers are even, so 2 works. 3 is also a factor, as are 4 and 6. But the greatest common factor, the granddaddy of them all, is 12. A good way to find the GCF is to first use prime factorization. 36 breaks down into 2 times 2 times 3 times 3. 48 breaks down into 2 times 2 times 2 times 2 times 3. The numbers that the 2 have in common are the 2 2's and a 3. Multiply those out and voila, 12. Practice finding LCMs and GCFs on your own and it will pay dividends. Just don't let the SITF catch you. Those guys are not to be trifled with.
What did the buffalo say to his son as he left for school?
Bye, son.
So that's the site I recommend that you guys go to if you ever need help on one of your subjects, that and perhaps Khan Academy. So let's go through some of the concepts that were in that video. Let's talk about what is a factor. The easiest way to describe a factor is by saying that it's a number that evenly divides another number. Alright, so for example, the factors of 6 are 1, 2, 3, and 6. This is because 1 times 6 is equal to 6. So we say 1 and 6 are factors of 6. And also 2 times 3 is equal to 6. So 2 times 3, both 2 and 3 are factors of 6. So they're numbers that multiply to give you an answer, another number. So that's what we were saying here, that factors can be multiplied together to get the number you want. So we'll do another example. Here we would say that 2 and 4 are factors of 8 because 2 times 4 is 8. Can you think of any other factors of 8? If you said 1 and 8, you are correct. So if I were to list all the factors of 8, they would be 1 and 8 because 1 times 8 is 8, and 2 and 4 because 2 times 4 is also equal to 8. And then I can't think of any other whole numbers that go into 8, so those are all the factors of 8. So let's go ahead and list the factors of 45. Well, the easiest one to get is 1 and 45, because you always know 1 times that number is equal to that number. So those are always going to be in your factor list. 1 in the number itself. Now I ask myself, does 2 go into 45? No, 2 doesn't go into 45. How about 3? See, I keep just going up the list. How about 3? I think about, wait a minute, yes, 3 times 15 is 45. So both 3 and 15 are factors of 45. I keep going through my list. How about 4? Does 4 go into 45? No. How about 5? Well, yes, this number ends in a 5, so I know that I can divide it by 5, And in fact, 5 times 9 is 45. And then I could keep going just to make sure I don't have it. Does 6 go into it? No. Does 7 go into it? No. Does 8 go into it? No. And now I can stop because does 9 go into it? Yes, but we already have 9 and all the numbers pass there. So let's do it again for 60. So let's list the easy one first, right? We know 1 times 60 is 60. Then let's go through our list. Does 2 go into 60? Yes, it does, 30 times. How about 3? Yeah, 3 goes into 60 20 times, so 3 and 20 are factors of 60. 4 times 15 is 60. 5 times 12 is 60. And finally, 6 times 10 is 60. So we list these in order, and all of these are the factors of 60. So now let's talk about a prime number. All right, a prime number is a number that only has factors of 1 in itself. So another way to think about it, it can only be divided by 1 in its own self. So let's think about the prime numbers up to 20. Now by definition, although 1 meets that definition, 1 is not considered a prime number. Alright, so a lot of people always think 1 is the first prime number. 1 by definition is not a prime number. The first prime number is 2. Right, the only factors of 2 are 1 times 2. The next prime number is 3, because only 1 times 3 is 3. Let's see, we go to check 4. No, 4 is not a prime number because 2 times 2 is 4, so it means it has more factors than just 1 and 4. But 5 is a prime number. Only 1 times 5 is 5. 6? No, 2 times 3 is 6. See, as soon as I find any other factors besides 1 in its own self, then it can't be a prime number. Alright, 7 is a prime number. Only 1 times 7 is 7. 8? No, it has factors of 2 and 4. 9 has factors of 3 and 3. 10 has factors of 2 and 5. 11. Only 1 times 11 is 11. 12 has several factors. Has 3 and 4 and 2 and 6, so it's not prime. 13 is prime. Only 1 times 13 is 13. 14? 2 times 7 is 14, so it's not prime. 15. People often get this one wrong by mistake, but 3 times 5 is 15. Oh, so it can't be prime. 16? Well, we have 2 times 8, we have 4 times 4, so it's not prime. 17 is prime because only 1 times 17 is 17. 18 is an even number. You know, in fact, after 2, notice that we have no other even numbers that will be prime because you can always divide an even number by 2. So after the number 2, no other even number is going to be a prime number. So it's only possible that an odd number is prime. So 18 is not going to be prime. 19 is prime. Only 1 times 19 is 19. And again, 20 is even number, so it can't be prime. Now, prime numbers do continue forever. That means there is an infinite number of prime numbers. As we get further and further, though, they become less and less prevalent. There becomes lesser and lesser of them close together. They're spread out quite a bit, but they do go forever. So right here, why don't we practice? Why don't we check all the numbers here that are prime? Take a moment and pause the video and do this on your own. Remember to ask yourself, can I divide it by anything else besides 1 in its own self? If the answer is no, then it's a prime number. Okay, so if you said 8 is not a prime number, good. 11, though, is prime. Only 1 times 11 is 11. 12 is an even number, so we could check it off as not being prime. 19 is prime. Only 1 times 19 is 19. 21. Nope. 21 has factors of 3 and 7, because 3 times 7 is 21, so therefore 21 is not prime. Notice that it's not like every single odd number is going to be prime. That's not the case at all. It's just that we know that every single number that's even number greater than 2 is not prime. That we can say for sure. And then 29. I can't think of anything besides 1 and 29 that equals 29, right? Let's see, 2 doesn't go into it, 3 doesn't go into it, 5 doesn't go into it, 7 doesn't go into it, so I can pretty much stop there. So these three numbers here happen to be prime. So how about we write 84 as the product of prime numbers? Now how come I can do this? How come I can take a number and write it as prime numbers being multiplied together? That is one of the properties of prime numbers. Turns out that any number that we have, any whole number, can be written as it's either prime itself, like 5, like 7, like we talked about, or we can write it as a product of prime numbers. That means I can find prime numbers that multiply to give me that number, and all the numbers in that list are prime. So when I'm asking you to write a prime factorization, is what I'm asking for is a list of prime numbers that when you multiply them all together, you get 84. And it will never be the case that you won't be able to do that unless the number itself is prime. So let's go ahead and start out. I'm going to start out by writing a factor tree for 84. Alright, so here I'm thinking of any two numbers I can think of that multiply to 84. Well, let me use a different color. So any two. And if I'm having a hard time trying to figure out numbers that multiply to 84, I look at the number and I notice that it's even. Okay, and I know that an even number is divisible by 2. Right? Any number that ends in 0, 2, 4, 6, 8, I can divide by 2. So without a lot of thought, I'm just going to put a 2 because I know 2 goes into it, and I know 2 is prime. And then I ask myself, what do I have to multiply 2 by to get to 84? Or when I divide 84 by 2, what do I get? All right, and in this case, you get 42. Right, and yes, 2 times 42 is 84. So that's what I mean by making our little factor tree. And it didn't have to be 2 and 42, it just can be any two numbers that you know to multiply to 84. But like I said, I couldn't think of any off the top of my head, but I knew 2 went in it, so I went 2. Same thing with 42. Well, I notice again that it is an even number, so I know 2 goes into it. How many times does 2 go into 42? Well, it goes in 21 times. 2 is prime, so I circle it. Notice if I tried to break down 2, the only two numbers I'd be able to find is 1 and 2. That's the definition of a prime number, so we stop there, right? I don't break it down until 1 times its own self. When I get to the part where it's prime, I circle it. Now I'm asking myself, can I break down 21? And yes, we can. We get 3 times 7 is 21. 3 is prime, and so is 7. So I circle the end leaves. These are all prime numbers. And so that we get that the prime factorization of 84 is 2 times 2 times 3 times 7. And yes, if you multiply these all together, you get 84. So that's what we call a prime factorization. Why don't you try this one on your own? Pause the video and see if you can write the factor tree of 60, resulting in 60 written as a prime factorization. Alright, so I'm thinking of any two numbers that multiply to 60. And it could be, again, there's more than one option, but any numbers you can think of that multiply to 60. So when I ask this student this question, the answer I get most of the time is 6 and 10. Because 6 times 10 is 60. Okay, so now I'm going to break down 6. I'm going to pick 2 and 3. Well, not pick. The only numbers that go into 6, right? It's only other factors besides 1 and 6 are 2 and 3. And they're both prime. Now I'm going to break down 10. Well, 2 goes into 10 5 times. And both of those numbers are also prime. Did I have to pick 6 and 10 here as my first products? No, you didn't have to. You could have picked 2 and 30. You could have picked 4 and 15. Whatever numbers you picked, it would have still broken down and given you these prime factors at the end. Now just to be nice, we go ahead and write them in order. So I notice I have 2 2's here, so I write 2 times 2, then times 3, and then times 5. So the prime factorization of 60 is 2 times 2 times 3 times 5. One more, let's do a final practice. Write 30 as the product of prime numbers. Alright, so let's grab any 2 numbers that multiply to 30. So how about 3 and 10? 3 is prime, so I'm going to circle it. Then I'm going to break down 10 into 2 and 5. We can't break them down anymore, so we say that our prime factorization of 30 is 2 times 3 times 5. We write them in order just to be nice, right? But technically, if they were switched, it would still be the same answer, as long as I have all the prime factors listed there, multiplied together. Alright, so go ahead and pause the video and see if you can do the prime factorization of 50 on your own. Alright, so this won't take us too long. We'll say 5 times 10 is 50. You could have also said 2 and 25. I just happened to choose those two. And finally, 10 is not prime, excuse me, I should not have circled it, right? 10 breaks down into 2 times 5. Alright, so that the prime factorization of 50 is 2 times 5 times 5. And you can always check that, right? 2 times 5 is 10, times 5 is 50. So you can always check, one way to check if a prime factorization is correct is to go ahead and multiply it out on the bottom, and you better get back to your original number. Right? And all the numbers in the list again have to be prime. So for example, if I gave you a test question and I had the prime factorization of 50 as being 2 times 25, that would be incorrect because 25 is not a prime number. Remember, every number in this list must be prime for us to call it a prime factorization. So let's go ahead and use this idea to solve a word problem. Suppose Eric is catering a party for 138 people. He wants to seat the same number of people at each table. He also wants more than 3 people, but fewer than 8 people at a table. How many people can he seat at each table? Then the hint is to use the prime factorization to help you solve the problem. Well, let's think about what I have underlined in this example here. He wants to seat the same number of people at each table. Well, if I'm going to seat the same number of people at each table, then I have to have a number that I can divide 138 into as a factor of 138. Right? It needs to be a factor. That means that number needs to be evenly divided by it. So, for example, 3. If we thought 3 would go into it, we could try to see, and we could divide it out. And then we could try 4, then we could try 5, and we could use brute force with that method until we found factors that were in between 3 and 8. But instead, why don't we go ahead and write out the prime factorization of 138, and we'll show you how to use this to solve this problem. Well, I'm trying to think of 2 numbers that multiply to 138. Again, I'm not quite sure what multiplies to 138 off the top of my head, but I know that it's an even number, so I know that 2 goes into it. Then if you had to pull out your calculator and take 138 and divide it by 2 to see what you get, you can go ahead and do that. And if you do that on a calculator, you'd get 69. Then I ask myself, can I break 69 down any further? And it turns out that yes, it's an odd number, so 2 doesn't go into it, but it turns out 3 goes into it. 3 goes into 69 23 times. because 3 times 23 is 69. So 2 is prime, 3 is prime, and it turns out 23 is also prime. So I can stop here. So now let's think about how I'm going to use this information to answer this question. Well, we can see this is divisible by 2, so I could split them into 2 groups and have these huge tables of 69 people apiece. But the problem says that it needs to be between 3 and 8, so that's too big. 23 obviously goes into 138, but then I'd have to have 23 people at each table. And again, the problem states that they need to be between 3 and 8. So 2 we already said is too small. How about 3? Well, the problem says here that he wants more than 3 people. So that means I can't have just 3. But remember, any combination, anything I can multiply together down here with these prime numbers is also a factor of 138. So notice here that I have the numbers 2 and 3 as factors of 8. Because both 2 and 3 are factors of 8, 2 times 3 is a factor of 138. It turns out that 2 times 3 is 6. And 6 is a number that is between 3 and 8. So it turns out that I could sit 6 people at each table and fill up all 138 seats with none left over. And if you really wanted to check that, go ahead and divide 138 by 6, and you'll see that you get 23 as an answer. Alright, so let's talk about greatest common factor now. The greatest common factor of 2 numbers is the largest number that you can divide them both by. Alright? So we call that the greatest common factor. It is the largest number that they both have in common as a factor. So let's do an example here. Let's say I wanted to find the greatest common factor of 20 and 25. Well, the greatest common factor of those 2 numbers is 5 because 5 is the largest number that will divide both 20 and 25. So the way that I know that is I can go ahead and list out the factors of 20. So remember, factors mean numbers that multiply to 20. So we get 1 in 20 because 1 times 20 is 20. We get 2 in 10 because 2 times 10 is 20. And finally 4 and 5. So those are all the factors of 20. Then I could go ahead and write out all the factors of 25, which are only 1 times 25, because 1 and 25 multiplied to 25, and then 5. Notice that 5 times 5 is 25, but I don't write that factor down twice. We just list it once as a factor. 5 is a factor. So now the greatest common factor is the largest number that appears on both of these lists. And here I have a 5 on the factors of 20 list, and I have a 5 on the factors of 25 list. And that's the greatest number that they share in common, so we call that the greatest common factor. So let's use that same strategy, that is making a list, to find the greatest common factors of 36 and 39. So in order to do that, I first start out by listing the factors of each number. So let's list the factors of 36. Well, 1 times 36 is 36. It's an even number, so 2 goes into it. 2 times 18 is 36. 3 will go into 36. 3 times 12 is 36. 4 goes into 36. 4 times 9 is 36. And then finally 6 goes into 36. 6 times 6 is 36. Notice I only list the 6 once. Okay, so those are all the factors of 36. Now let's go ahead and list all the factors of 39. We get 1 times 39 and 3 times 13. And 39 has no other factors. So now if I want to find the greatest common factor between these 2 numbers, recall that it is the largest number on both lists. Well, they have a 1, they have a 3. Let's see, here's a 13. There's no 13 as a factor of 36 though, and there's no 39. So it's looking like 3 is the winner here. Right? The largest number on both lists is 3. So we say that the greatest common factor of 36 and 39 is 3. So go ahead and pause the video and take a moment to find the greatest common factor of 12 and 36 by listing out all their factors and finding the largest number on each list. Alright, let's start by listing the factors of 12. Factors of 12 are 1 and 12, 2 and 6, and 3 and 4. The factors of 36 are 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6. So now let's find the largest number that is on both of these lists. Well, as a factor of 12, I see that 12 is a factor of 12, of course, and 12 is also a factor of 36. And it is the largest number on both lists, so that we say the greatest common factor of 12 and 36 is 12. Now, making a long list of factors can be time-consuming, right? Especially if the numbers are large numbers, right? There must be a better way to find the GCF besides making these long lists of numbers. And luckily for us, there is, and that's using the prime factors. You know, I didn't show you guys that stuff for anything, for nothing. So think about if I had two 3-digit numbers. I might not want to make a list of all their factors and then find the largest factor on both lists. Or what if I had a number that was in the thousands, tens of thousands? That would be really time consuming. So let's talk about how we can solve for the greatest common factor using prime factors. We're going to go ahead first and we're going to find the prime factorization of each number. So we did plenty of examples like that, so we're going to go ahead and do our factor tree here. And let's do this one again, the GCF of 12 and 36. We just did that problem. We saw that it was 12 when we listed out all the factors. Now let's do it this way. So the factors of 12 are 2 and 2 and 3. That's what we'd call the prime factorization of 12. Alright, then I go ahead and get the prime factorization of 36. So I thought of two numbers that multiplied to 36, which were 6 and 6, and then I broke each of those down to 2 and 3 and 2 and 3. And then I stopped because that is their prime factors. Alright, so how do we find a greatest common factor now? Is what you're looking for, alright, is numbers that are shared between both lists. So whenever the two numbers share a factor, we write that factor down once. Then when we're done making all the pairs we can, then we multiply the result, and that's how we find out what our greatest common factor is. So notice I have a 2 listed as a factor of 12 and also a factor of 36. So I go ahead and I'm highlighting the 2's here and I'm writing the 2 down once. Now I'm looking between the two numbers again and I'm saying, okay, now is there anything else? Can I make any other pairs? And notice here I have a 2 over here and another 2 as a factor of 36. So I go ahead and highlight those and I write that number down once. How about 3? Yes, I have 3 that appears on both lists. So I'm going to write that number down once. And then there's no other pairs that I can make. I've used them all up. So now finally all we do is multiply those numbers together, 2 times 2 times 3, and we get 12. So let's go ahead and let's see if we can find the greatest common factor of 24 and 60 using the prime factors. Alright, so here I'm breaking down 24 into its prime factors. So I went ahead and I said, well, 2 times 12 is 24, 2 is prime, 3 times 4 is 12, 3 is prime, and 4 breaks down to 2 times 2. Alright, so the prime factorization of 24 is 2 times 2 times 2 times 3. Now I need to do the same thing with 60. So I go ahead and break it down. If you need more help on prime factors, go ahead and look at the beginning of this video. So here 60 breaks down into 2 times 2 times 3 times 5. Those are the prime factors of 60. Then remember what we're trying to do here. We're trying to find numbers that appear on both lists. I'm trying to find pairs. So here notice I have a 2 and I have another 2. So I go ahead and pair them up. I have a 2 here and another 2 that I can pair up over there. Then finally I have a 3 and a 3 on this list. Notice I'm looking for pairs between the numbers, not within the number. I'm not writing down a pair this way. You know, we're not doing that. We're looking between the numbers that we're making pairs. Right? So it's those numbers that I'm pairing up. Whenever I have a pair, remember I write that number down once, and then we multiply our result. So I had a pair of 2's. That's where this red 2 came from. I have another pair of 2's between the numbers. That's where this green 2 came from. And then 3 paired up with this 3, and I couldn't make any other pairs. So then once I'm done doing that, I just multiply those numbers together, and I get 12. Alright, and 12 is the greatest common factor between 24 and 60, because 12 times 2 is 24, and it turns out 12 times 5 is 60. Alright, so 12 is indeed a factor of both of these numbers. Now let's talk about the difference between that and what we call a multiple. So we saw that a factor is a number that will divide a number, or two numbers that multiply to give you another number. You know, that would be factors of a number. Whereas multiples of a number are the result of multiplying a number by an integer. So it's like counting by, for example, in this case, 5s. We would say the multiples of 5 are 5, 10, 15, 20. We could keep going 25, 30, 35, 40 forever. Right? Because 5 times 1 is 5. 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. And we can do that forever. So those are called multiples of a number. So let's list at least 5 of the multiples of 7. So I'm really asking you to start counting by 7s. So go ahead and take a moment to think about and write out the list of the first 5 multiples of 7. Right, so if we start counting by 7s, we're going to get 7s, 14, 21, 28, 35, 49. We could keep going, right? 7 times 8 next to give you 56, and so forth. Now, so when we're talking about the least common multiple then of two numbers, that's basically just the smallest number that both numbers multiply into equally. All right? So imagine if we go ahead and make our list of numbers again. So we're going to make a list of the multiples of one number, and then make a list of the multiples of another number. We're trying to find the largest number, the smallest number on both those lists. So consider 8 and 10, and we're to ask the question, what is the least common multiple of 8 and 10? Well, one way to do it, and this is the brute force method, right, is to start listing out the multiples of 8. Alright, so they're 8, 16, 24, 32, 40, 48. We could keep going forever, right? Then I start listing out all the multiples, not factors, that multiples of 10. And those are 10, 20, 30, 40, 50, and so far forever. But as soon as I get to 40, I can kind of stop because I see that 40 is the smallest number that appears on both of these lists. So one way to think about it, here's an 8 as a multiple of 8, but there's no 8 as a multiple of 10. And 16 only appears on this list, and so forth. So I'm looking for one to match, and we can see that 40 is the smallest number I can find that could match. Now if I kept going on, I would find other multiples of both 8 and 40, but they just wouldn't be the least common multiple. Alright, so go ahead and let's practice. I want you to pause the video and find the least common multiple between 6 and 15. And I want you to do this by making a list of all the multiples of 6, then making a list of the multiples of 15, and finding the lowest number that is in common in both lists. Alright, so I'm going to go ahead and start listing out the multiples of 6. So we get 6, 12, 18, 24, 30, 36. We could keep going, and if I have to, I will, but let me start going ahead and writing out the multiples of 15. Alright, so 15, I'm going to go 15, 30. The next one would be 45, but I can stop after 30 because I notice that I have a factor of 33 on my list of multiples of 6. And I have a multiple of 30, sorry, I have 30 as a multiple of 15 on my second list. So 30 is the smallest number that appears on both of these lists. So we say that the least common multiple of 6 and 15 is 30. So again, if I found the least common multiple of 3 and 2, I could list the multiples of 3 as 3, 6, 9. Keep going if I want to, 12, 15. I could list the multiples of 2, 2, 4, 6. Then we can stop, because we can see that 6 on this list, and 6 is on this list, and therefore it is the lowest number on both lists, and so we call it the least common multiple. But again, making lists of multiples can be time consuming, right? There must be a better way. And luckily for us there is, using prime factors again. I didn't show you guys that stuff for nothing. So let's think about finding the least common multiple of 8 and 10 using prime factors. So when we made the list, we already saw that the least common multiple of 8 and 10 is 40. Now let me show you how to get that number 40 using prime factors. So again, just like before when we were finding the greatest common factor, I go ahead and I make the factor tree for 8, or get its prime factorization. And we see that the prime factorization of 8 is 2 times 2 times 2. Then I go ahead and I break down 10. Well, the only factors of 10 are 2 and 5, and they're both prime. Okay, so now I've listed here the prime factorization of both 8 and 10. So in this case, this is very close to finding the greatest common factor. Right, we're going to start off in fact the same way. So I'm looking for pairs. I'm looking for numbers they share in common between both lists. And notice that right here I have a 2. And in this list I have a 2. Alright, so is what we're going to do, I'm looking for any other pairs. So I have, here's a 2, but I have no other 2's. So I'm done. I only had one pair. So now if I was finding the greatest common factor, I would say that it was 2. You know, I'd write down the 2 once. But this is where it differs when I'm finding the least common multiple. Is what we do is I find the ones they have in common and I write them down once. And then we have to write down whatever is left over and we write it down once. And then we multiply all the numbers together, and then that's how we get our answer. So this 2, this first 2 I'm writing is because I have a pair between 8 and 10. They have the 2 in common. And then once there's nothing left in common, I write down what's ever left over once. So this 2 is from here. This 2 is because of that. And this 5 is because of that. Remember, those were all the ones that were left over that I couldn't pair up with anything else. So then I write them down once. And then finally I have to multiply everything together. And 2 times 2 times 2 is 8, times 5 is 40. So the least common multiple of 8 and 10 is 40. Take a moment and pause the video and see if you can use prime factorizations to find the least common multiple of 15 and 20. Alright, so I find the prime factorization of 15, which is 3 times 5. I then go ahead and break out down 20 into its prime factors, which is 2 times 2 times 5. Now I'm looking, remember I'm looking for pairs, numbers they share in common between both lists. So the first thing I look at this 3 as a prime factor, it's one of my factors of 15, and I look over here at 20 and I don't see a 3 in that list. So now I check 5, and yep, I see that both lists do have a prime factor of 5. So remember, when they have something in common, I write it down once. So there's my 5. Both of these 5s together, then we wrote down just one 5 for that. And then now notice what was left. We have 2 2's. Okay, so here they are on my list, 2 and a 2, and then also a 3. And there's my 3. So anything that was left over, I wrote it down once. And then we multiply our result together to get 60. So the least common multiple of 15 and 20 is 60. And if we were to go ahead and make our list of the numbers, you would see that it was 15 times 4, which is 60, and 20 times 3 is 60. And that's the lowest multiple of each of those numbers that they share in common. So now let's go ahead and use least common multiple to solve a word problem. Suppose Bob and his son are jogging around the track at a school, and Bob completes a lap every 3 minutes, and his son completes a lap every 5 minutes. They start at the same time. Right? How many minutes will they be together at the starting line again? So whenever you see these kind of problems where one person's doing something at one rate or something's happening at a certain interval and then something else is happening at a different interval and we want to know when they'll be the same, that's your hint that it's a least common multiple problem. Other type of problems that involve least common multiple are, say, if I have hot dogs versus hot dog buns. You notice how hot dogs come in packs of 6 and hot dog buns come in packs of 8. So we might ask, how many hot dogs would I actually have to make so that I use all the packages of hot dogs and all the packages of hot dog buns without any leftover? That's a least common multiple problem. You'd be trying to find the least common multiple in that case of 6 and 8. In this case, I'm just trying to find the least common multiple of 3 and 5. So remember, what I would start out doing is listing the prime factorization of 3. But 3 is already prime, because only 1 times 3 is 3. Then I would find the prime factorization of 5, which again, 5 is prime, is only 1 times 5. So remember, I don't have anything in common between these two lists, so then I end up just multiplying those together. What's ever left over together, and 3 times 5 is 15. So that means that Bob and his son will be together again at the starting line after 15 minutes. And you could see that, because you could see that Bob is running this track every 3 minutes. So he would pass the starting line after 3 minutes, then 6, then 9, then at 12 minutes he passes it again, then at 15, and then again at 18. So we could keep doing this forever, assuming that Bob never runs out of energy. Okay. Now I could go ahead and start making the list for his son. He completes his first lap after 5 minutes. Then it would be after 10 minutes. Then it would be after 15. Wait, stop. At 15 minutes, Bob is passing the starting line and also his son at the same time. So that's what we said. They'll be together again at the 15-minute mark. And that's just a least common multiple problem of finding the least common multiple between 3 and 5 in this case. So that concludes today's session. Remember to log on to your session questions, which you can find in the course announcements. So in the course announcements, you will find where it says Asynchronous Session 2. Make sure to click underneath this link where it says the asynchronous questions. Complete those questions and submit them. If you have any questions, please message or email me. Thank you.